In this video, we take a first stab at establishing some of the basic rules that we can use for counting. The rule of products is something that we're going to use anytime we're counting finite structures where the order matters. The general statement is that if you imagine us creating a process for filling in two blanks where there are X choices for the first blank and Y choices for the second blank, then if you were to go through and make all possible choices in all possible ways for those two steps, then you would have a total of X times Y things that you have filled in. This is exactly the same thing that we saw in Chapter 3 when we looked at the size of the Cartesian product of two sets. At that time, we said that the Cartesian product of the size of the Cartesian product of A and B has the size that's the size of A times the size of B. The reason that we're not stating this that way is because in our problems, and in most of the problems that we do, we're going to want to have more than just an ordered pair. And so we're going to want to normally have 3 or 4 or 5 or more blanks to fill in. And if we think of it in terms of creating a number of steps for filling in the blanks, then we can extend that to any number of blanks. So for example, this is a very contrived example using numbers. So these are 3-digit numbers. We often use these when we're counting things where the order matters, because everyone believes that the order of digits matter in terms of the value of the number. So everybody believes that 153 is different from 135. So we don't have to have any ambiguity there. So if I'm building 3-digit numbers, I can imagine that happening by filling in 3 blanks. So I have 3 blanks, and I want to imagine a process, a 3-step process, where I first, oops, that's not the right thing, where I first choose a digit. I am struggling with my controls. Hang on. So we can think about filling in these blanks in terms of a 3-step process. So I could have step 1 be choose a number for the first blank, and so that means I'm going to put a number there. Notice that that's just after that step. I haven't built any 3-digit number yet. I've only filled in 1 digit. Step 2 would be fill in the next digit. I mean next left to right. And step 3 would be fill in the last digit. So I would do steps 1, 2, and 3 in order to create one 3-digit number. And then the idea is, if I do steps 1, 2, and 3 in all possible ways, in other words, all possible combinations of choices, then I will produce all the numbers that that I'm trying to count. So that is the first part of the rule of products, is that I have to have a multi-step process for building one of my finite structures, and I'm going to count how many steps there are, or how many ways there are to complete each step in that process. And so that's half the battle. The second half of the battle is, am I able to do the analysis where I can tell you how many choices I have for each step? Well, in the first step, that's pretty easy. I'm just choosing a number 1, 3, 5, 7, or 9, so there are 5 choices for that. Step 2 is a little more subtle, because I'm still choosing numbers from 1, 3, 5, 7, 9, but I have this condition that I want the digits to be distinct. So I don't want to repeat any digits. And so that means that whatever I've chosen, so maybe I put a 7 here, whatever I've chosen for that first blank, I now only have 4 choices for what can go in the next blank, because I'm not allowed to use whatever I picked first. So in my example, I would not be allowed to use 7 to fill into the second blank. Notice that if I made a different choice in step 1, then I would have a different set of 4 choices for step 2. But no matter what I do in step 1, I will always have 4 choices. There'll never be a different number. It'll always be 4. It won't be the same 4, but I'll always have 4 choices for step 2. And then finally, and if it helps, you can sort of do it as you go, so you can sort of visualize what it's saying. So perhaps I pick 7 for the first number and 5 for the second number, and now I have to pick a different digit for the third number, and so you can see I now have 3 choices for that. And again, it won't be the same 3 choices regardless of what you do before, but it'll be 3 choices no matter what. So if we can do that, if we can actually count the number of ways to make each decision, and we know that so just to completeness, I'll pretend like that's a 1. So if I have the number of options for each step, and I know that going through the steps in all possible ways generates what I want to count, then my conclusion is that my total is just the product 5 times 4 times 3. So that is, what is that, 60. So that seems a little abstract. So 60 is not a terribly big number. I wouldn't list them all to count them, but I did list them all so that we could see how this algorithm is actually producing. So here you can see all 60 possibilities, and notice that I've organized the table so that all of those first choices, remember the first choice we made was what is the first digit, and so the first choice, so step 1 is basically telling us which column we're in. Right, when we decide what our first digit is, it's deciding which of these columns you have. Step 2, once you're in a column, step 2 is picking the second number, and you can see how this has been partitioned. So I have these blocks for each possible second number, and that's true for every column. All these blocks have the same second number, and so on. So step 2 is picking which of these blocks you're in, and then step 3 is picking which of the numbers within the block you're in. So you have 5 columns, each column has 4 blocks, and each block has 3 numbers. So it's easy to see why 5 times 4 times 3, the multiplication of those, is actually counting all of the possibilities here. So here's an example. Suppose we have an organization that has 10 male and 7 female members. The first question is, just in how many ways can we organize, how many ways can we elect a president, vice president, secretary? I use this example right off the bat because it makes us have to think about representation. When we're doing these problems where in the structure the order matters, more times than not, I'm going to try to represent outcomes as a series of fill in the blanks. So in this case, I would have to decide what order I'm going to list my officers, but an election result would essentially be just filling in 3 names into these blanks. If we just decide ahead of time that the convention is the first name is the president, the second name is the vice president, the third name is the secretary, then we can just list the 3 names and that would be a representation of the outcome. In that representation, the order matters. If you switch 2 names, that's 2 different election results because those people would have different offices. And in a normal organization, you would have the implicit rule that one person shouldn't serve in 2 different positions. I know in some small clubs that doesn't happen, but we assume here that one person can't hold 2 positions, and so we would not have repetition. So this is the permutation problem we talked about in section 5.1. Our algorithm for counting this would just be choose a president, choose a vice president, and choose a secretary. In other words, I'm going to fill in the blanks left to right the same way that I did with our digits. There are 17 choices for step 1 because I can pick anybody at all to be the president. There are 16 choices for step 2 because I have to pick a different person, so it can be any of the other 16 people. And then there are 15 choices for step 3. So 17 times 16 times 15 will be the product of the number of ways to do these steps. And so that'll be the total number of election outcomes I could have. Now you see I've covered some things up here because I have some other conditions that I'm interested in. And this happens all the time, especially in the context of probability, where we'll be applying this stuff. So my first condition I want to talk about is how many of these are there if the president must be female? Well, notice that that doesn't change the three-step algorithm as being a correct way to represent things. All the condition that the president must be female, oops, the only thing that condition does is change the number of choices we have for step one. It does not change the steps, it just changes the analysis of how many ways there are to do that step. So in this case, if I want the president to be female, then when I choose the president, I only have 7 choices. So I have 7 choices for step one. There is no restriction on the vice president, so it can be any one of the other 16 people in the club. And there's no restriction on the secretary other than it can't be either of those 2 people, so it can be any of the 15 other people in the club.